Modules and Homological Algebra Lecture 15, Adjoint Functors. Definition. Let C and D be two categories. Let F be a functor from C to D, and let G be a functor from D to C. We say that the pair F, G is an adjoint pair of functors, provided that for any object I in the category C and any object j in the category D, there are isomorphisms alpha ij between the set of all morphisms in D from fi to j and the set of all morphisms in C from I to g of j, and these isomorphisms alpha should be natural in both I and j. Note that we say isomorphisms alphas are just maps between two sets. Saying that alpha is an isomorphism is exactly the same as saying that alpha ij is a bijection. The terminology: in this case, the functor f is called the left adjoint of G, and the functor G is called the right adjoint of f. Let us now explain what do we mean when we say that these isomorphisms alpha should be natural in both I and j. Naturality in I means that for any morphism H in C from I to I prime, the following diagram should commute. So we can start in the morphism set in D from f of I prime to j, and from this set we have two maps. We have the precomposition with f of h, which sends us to D f of ij, and we have our isomorphism alpha with indices I prime j, which sends us to C I prime g of j. From the set D f of ij, we can use alpha ij to go to C I g of j. And to the same set, we can arrive from C I prime g of j using the precomposition with h. These two different paths should coincide for all h from I to I prime, and this means naturality in I. Similarly, naturality in j means that for any h, a morphism in D from j to j prime, the following diagram should commute. So now we start from D f of ij, and from here we can use our alpha ij to go to Ci g of j, or we can use the postcomposition with h to go to D f of ij prime. From D f of ij prime, we can use alpha to go to Ci g of j prime, and to the same set we can come from Ci g of j by using the postcomposition with g of h. So the two paths in this diagram should coincide, and this means naturality in j. Here is the first example. It's about equivalences of categories. Assume that f from C to D is an equivalence with inverse G. Then we can start with the morphism set in D from f of I to j and apply our equivalence G, and this gives us an isomorphism from this set to the set of all morphisms in C from G of f of I to G of j. And this isomorphism is natural both in I and j because of the functoriality of G. Now, since the composition of G and F is isomorphic to the identity functor on C, this is because we assume that F and G are mutually inverse equivalences of categories. It follows that the second summoned here, morphism set in C from G of f of I to G of j, is actually isomorphic to the morphism set in C from I to G of j, because G after F is isomorphic to the identity functor. So we have an isomorphism between D f of ij and C I g of j, which is natural both in I and in j. This proves that the pair f, g is an adjoint pair of functors. Note, in this case, G is also an equivalence, so exactly the same argument says that the pair G, f is also an adjoint pair of functors. In other words, any equivalence between two categories is both left and right adjoint to its quasi-inverse. Here's a more advanced example. Let us talk about free functors. Consider the category monoids of all monoids and monoid homomorphisms. Then we have the forgetful functor, let's denote it by G, from the category of monoids to the category of sets, which takes a monoid and sends it to its underlying set. And we also have the free functor curly f from the category of sets to the category of monoids, which sends a set to the free monoid on this set. The adjunction axiom then asserts that the homes in the category of monoids from a free monoid on X to any monoid M, these homes are isomorphic to the set maps from X to the underlying set of M. And this is exactly the free property of the free monoid f of x. So the adjunction here between the free functor and the forgetful functor is simply equivalent to the free property of a free monoid on a set. And it's very easy to see that this isomorphism is natural in both x and m. This follows directly from the definitions. And so the free functor curly f is left adjoint to the forgetful functor g. And let's note that, unlike in the previous example, here we have a free functor which is left adjoint to the forgetful functor, and usually free functors are not right adjoint to anything, so they are just left adjoint. And the same thing holds, of course, for other algebraic structures, like groups, algebras, etc. Next, we would like to establish uniqueness of adjoint functors, and for this we need to discuss the category theoretical statement, which is called Yoneda lemma. Here is the covariant version of the Yoneda lemma. Let C be a category and F a functor from C to sets. Then, for any object I in C, we have an isomorphism which is natural both in this object and in the functor f. The isomorphism takes place as follows. We consider the category of all functors from C to sets. This is a category, as we know from the previous lecture. And in this category we have two functors. The representable functor Ci blank, associated to the object I, and our functor f. So the set of natural transformations from the representative functor Ci blank to f is isomorphic to f of I. That's the claim of the lemma. And we also have the contravariant version of this lemma. Let C be a category and G a contravariant functor from C to sets. Then, for any object I in C, we have an isomorphism which is natural both in this I and in the functor G. This isomorphism takes place in the category of all contravariant functors from C to sets, and it says that natural transformations from the representable functor C blank I to the functor G is isomorphic to G of I. So we will prove the covariant version of the lemma, and the contravariant version is an exercise. So let H be a morphism in C from I to J. Then, for any natural transformation eta from the representable functor Ci blank to f, we have the commutative diagram as follows. We can start from Cii and use the postcomposition with H to go to Cij, or we can use eta I to go to f of I. Starting from f of I, we can use f of h to go to f of j, and to f of j we can also arrive from Cij using eta j. And the two paths in this diagram should coincide. Indeed, the commutativity of this diagram follows directly from the fact that eta is a natural transformation. That's just the definition of a natural transformation. So this commutative diagram, on the one hand, sends the identity at I to eta j of h. So this is if we go first here and here. And if we go the other way around, we will get that identity of I is sent to f of h of eta I applied to 1 of I. In other words, this means that the value of eta j on h is completely determined by the value of eta I at the identity on I. Moreover, by choosing the value of eta I at the identity on I, we uniquely determine eta j of any h and define in this way a natural transformation eta. So this means that such natural transformations are indeed in bijection with elements of f of I. And the naturality here follows directly from the construction. Now we can use Yoneda lemma to discuss uniqueness of adjoint functors. Proposition: let f, g and f, g prime be two pairs of adjoint functors. Then g is isomorphic to g prime. Similarly, let f, g and f prime, g be two pairs of adjoint functors. Then f is isomorphic to f prime. Proof: we prove the first statement, and the proof of the second statement is similar. So since f, g and f, g prime are two adjoint pairs of functors, then we have isomorphisms between ci j of j, d f of ij, and ci j prime of j. And this isomorphism is natural both in I and j. If we look at the first and the third expression, we have an isomorphism here which is natural in I. It means that the functors c blank, g of j and c blank, g prime of j are isomorphic. And this isomorphism is natural in j. By Yoneda lemma, we have that the corresponding objects g of j and g prime of j must be isomorphic, and this isomorphism is natural in j. But this means exactly that the functors g and g prime are isomorphic. Next, let us discuss a special natural transformation which exists for any pair of adjoint functors, which is called the unit of adjunction. Let f, g be an adjoint pair of functors where f is a functor from C to D. Then, for any I in C, we have an isomorphism between the set of all morphisms in D from f of I to f of I, and the set of all morphisms in C from I to g of f of I. That's just a definition of adjunction. So let us denote by eta I the image of the identity on f of I in the set of all morphisms in C from I to g of f of I under this isomorphism. The claim that the collection of these eta i's for all I in C is a natural transformation from the identity functor on C to the composition of G after F. Proof: if H is a morphism in C from I to I prime, then we have the diagram. So H goes from I to I prime, and then we can use eta I prime to go to G of F of I prime. Alternatively, we start at I, go by eta I to G of F of I, and then we use G of F of H to go to G of F of I prime. And due to naturality of these isomorphisms, this diagram commutes. And this means exactly that eta is a natural transformation. So this natural transformation eta is called the unit of the adjunction. Similarly, we have the co-unit of our adjunction defined as follows. Let f, g be an adjoint pair of functors where f is a functor from C to D. For any object j in D, we have the isomorphism between the set of all morphisms in C from g of j to g of j, and the set of all morphisms in D from f of g of j to j. Denote by epsilon j the image of the identity on g of j in the set of all morphisms in D from f of g of j to j under this isomorphism. Note that here we apply the inverse of alpha. Alpha goes from d something to c something, and here we go back. So to get epsilon j, we should apply alpha inverse to the identity at g of j. Similarly to the previous slide, this epsilon is in fact a natural transformation from the composition of f after g to the identity on d. And we have the same proof for any morphism h in d from j to j prime. We have the following diagram. So we can start from f of j and go by epsilon j to j and then by h to j prime. Alternatively, we go by f of g of h to f of g of j prime and then go by epsilon j prime to j prime. And this diagram commutes due to the naturality of this isomorphism. And this means that epsilon is a natural transformation. And this natural transformation is called the co-unit of the adjunction. And for the unit and the co-unit of the adjunction, we have the following identities. These natural transformations eta and epsilon are called adjunction morphisms. Theorem, which is usually called adjunction identities. The following composition coincides with the identity natural transformation on f. So we start at f, we apply f of eta, and we go to f after g after f to this composition, and here we apply epsilon of f and go to f. This composition coincides with the identity natural transformation on f. Similarly, the following composition coincides with the identity natural transformation on g. We start from g, we apply eta evaluated at g to go to g after f after g, and here we apply g of epsilon to go to g. And this composition is the identity natural transformation on g. As usual, we prove only one of these identities, and the other one is an exercise. So here we prove the second identity. So we need to prove that g of epsilon after eta restricted to g is isomorphic to the identity on g. So first of all, let's use the definition of eta and rewrite eta restricted to g as the image under alpha of the identity on f after g. So what we want to compute is equal to g of epsilon after alpha applied to the identity on f after g. Now if you look at this composition, we can use the naturality of alpha, because here we have g of epsilon after alpha of something, so we can rewrite it as alpha of epsilon after the identity on f after g. So this is exactly the naturality of alpha. So here we have something after identity, so we can just delete the identity because it's the identity morphism. So the whole thing becomes alpha of epsilon. And now we recall that we defined epsilon as alpha inverse of the identity. So alpha of epsilon gives us exactly the identity on g. That's the definition of epsilon. And this completes the proof. And the most interesting thing about the adjunction is that the adjunction identities really determine the adjunction in the following sense. Theorem: let f be a functor from c to d and g a functor from d to c. Assume that there are natural transformations eta from the identity on c to g after f and epsilon from f after g to the identity on d, which satisfy our adjunction identities. So the composition of f of eta followed by epsilon restricted to f coincides with the identity on f, and the composition of eta restricted to g followed by g of epsilon coincides with the identity on g. Then f, g is an adjoint pair of functors. In order to prove this theorem, what we do, we construct our isomorphisms between the home sets as in the definition of the adjoint functor. Let H be a morphism in D from f of I to j. What we can do, we can apply G to H to get a morphism G of H in C from g of f of I to g of j. If we precompose this with eta I is a morphism from I to g of f of I. If we precompose it with eta I, we get a morphism g of h after eta I, and this will be a morphism in C from I to g of j. And in this way, we define our map alpha. Starting from h, which is a morphism from f of I to j, we get this composition, which is a morphism from I to g of j. This is our map alpha. Now about its inverse, we start from h, which is a morphism in C from I to g of j. We apply f, we get a morphism f of h in D from f of I to f of g of j. And now we can post-compose with epsilon j to get epsilon j after f of h, and this will be a morphism in D from f of I to j. And this defines a map from ci g of j to df of I j, which we denote by alpha inverse. Of course, the notation is suggestive, so we claim that alpha and alpha inverse are mutually inverse bijections. So we need to check that alpha inverse after alpha is the identity and alpha after alpha inverse is the identity. So we check one of them and the other one is similar. So we want to prove that alpha inverse applied to alpha of h is equal to h for any h. Recall that what is alpha of h? Alpha of h is g of h after eta I. And then when we apply alpha inverse, we should apply f to this and then post-compose with epsilon j. And we want to prove that all this thing is equal to h. We can draw all this on the following diagram. So we have f of I, we have f of eta I, which goes to f of g of f of I, and then epsilon f of I, which goes to f of I. We have h, which goes from f of I to j. We have f of g of h, which goes from f of g of f of I to f of g of j. And we have epsilon j, which goes to f of g of j to j. Now we can complete the left side to the triangle by defining the map from f of I to f of g of j to be the composition of f of eta I followed by f of g of h. And since f is a functor, this is f of g of h composition with eta I. And that's exactly the second map here in our identity. And then we have here the square on the right, and it commutes because epsilon is a natural transformation. Great. So the whole diagram commutes, and we see that the left-hand side in our identity is exactly the path here from f of I, the lower perimeter path. We go directly from f of I to f of g of j, and then we go to j. This gives us epsilon j after f of g of h composition with eta I. And here we have the upper pass on our perimeter, which starts with the adjunction identity and then goes by h. And we know that the adjunction identity gives us the identity morphism, so the upper pass just gives h. So our identity, which we need to prove, reduces to the commutativity of this diagram. Great. Let us discuss some further examples. Example 1. Assume that f and g are mutually inverse equivalences between C and D. Then the unit eta, which is a natural transformation from the identity on C to the composition of G after f, is in fact an isomorphism of functors. This is because G after f is actually isomorphic to the identity on C. Similarly, the natural transformation epsilon from f after g to the identity on D is an isomorphism of functors. Here's another example, example 2. Consider the zero functor from the category of abelian groups to itself. This functor maps any abelian group to the zero abelian group and any morphism of abelian groups to the identity morphisms on the zero group. Then, of course, 0, 0 is an adjoint pair of functors. So the zero functor is left and right adjoint to itself. And in this case, both eta and epsilon are the zero morphisms. Here are some problems and questions at the end. Question 1. Prove with all details the contravariant Yoneda lemma. Question 2. Prove with all details uniqueness of left adjoints. Question 3. Check that isomorphism of two functors f and g is equivalent to the collection of isomorphisms f of I is isomorphic to g of I for all I that are natural in I. Question 4. Check with full details the argument about naturality of adjunction in the definitions of the unit and the counit of the adjunction. Question 5. Prove with all details the first adjunction identity. Thank you very much and see you next time.